Hello, my name is Zachary Johnson, and today I will be talking about stellar evolution. Ever wonder how stars got to where they are today? They didn't just pop into existence like this, it took them millions, if not billions, of years. Stars are living things, not static forces at all. You can actually think of them like people, and that makes it easier for a lot of actual people to understand. Or like a year, that works too. I like a year because I want to work something into this that doesn't work with an example of a person. So how does a star's life begin? Much like the new year, with several explosions. People ring in the new year with explosions in the sky. Funny enough, that's how most stars are rung in, but the explosions are several orders of magnitude larger. It might seem weird to start a video with seemingly the end of a star's life, but a supernova is how a lot of stars get their beginning. Briefly, a supernova is when an incredibly large star can no longer fuse elements within its core, and it basically collapses in on itself in a massive explosion. This releases a lot of energy, which over time coalesces into large masses of cold and dark mass. This is called an interstellar cloud. These interstellar clouds aren't what you'd expect from a cloud. They're large, rich in mass, and can fit thousands of Earths in them, not the other way around. Over time, these interstellar clouds, much like their predecessors, begin to collapse under their own weight. Thankfully, they can explode, but the interstellar cloud does break up into smaller fragments. Going back to the year, this is kind of like Valentine's Day with the breaking up and everything else. Maybe I've just had bad Valentine's Days. Anyways, given time, these fragments get hotter and denser, and eventually they form protostars. And here is where a year splits into two paths, or star, if that's how you roll. An important distinction needs to be made here that will determine the entire lifetime of a star, its full birth, lifespan, and its death. Here's the difference. The mass of the star. What a quick side note here. Brown dwarfs. These are clumps of mass that just weren't quite big enough to initiate hydrogen fusion, and eventually cooled down from their original heating up. They are spherical in nature, but they don't share anything else with stars. They hardly emit any light and heat, and they just kind of float around being failures. And it's estimated that there are as many brown dwarfs as there are true stars in our galaxy. Going back to the year, think of them like a weekend that you could have sworn was a 3-day weekend, but it wasn't. There are big stars and there are little stars. We're in March right now, and all the fireworks have stopped, going back to the year analogy. Everyone has kind of made a plan for the year, and true star formation can begin. Depending on the size of the interstellar cloud that formed the actual star, a star could either be a low mass star or a high mass star. The differential between the two is about roughly 8 solar masses. High mass stars, shockingly enough, are far larger than the small mass stars. Let's start with the low mass stars. These are the guys that have their whole year planned out, know exactly what they want from each day, and make the most out of their time. Their formation is complete with the beginning of hydrogen fusion, which is when the star is massive enough to fuse hydrogen atoms within its core, which produces ginormous amounts of energy and heat. There are multiple types of low mass stars. There are your yellow dwarfs, like our sun. There are red dwarfs, who last a long time. And there are orange dwarfs, who don't get talked about a lot. There's a lot of these low mass stars, but they aren't flashy, and because of that, they don't get a ton of attention. Ironically, the only confirmed bit of life runs on them, which, is ironic because these low mass stars are usually ignored. And now we move on to our high mass stars. These are the stars with a mass greater than 8 solar masses. These guys are a bit more reckless than the low mass stars, and they're a bit less reserved. They're the type to kind of not really know what's going on, bleed through the days, and do whatever they want. As a result, they burn bright, are fun to watch, and they can cause a lot of things to happen. However, they're not that dependable and will be gone in a fraction of the time as the low mass stars. Types of high mass stars are blue giants, red hypergiants, and blue hypergiants. Having made this distinction, we return to the shared path. So after the formation of star, it enters its main sequence stage. This is basically the summer. Everyone wants to be in summer all the time. No responsibilities, no worries, just good times, and summer ends up taking a good portion of the year. Speaking of summer, there's 104 days of summer vacation, and school comes along just to end it. So the annual problem for our generation is finding a good way to spend it. Like maybe building a rocket, or fighting a mummy, or climbing up the Eiffel Tower. Discovering something that doesn't exist, or giving a monkey a shower. Surfing tidal waves, creating nanobots, or locating Frankenstein's brain. Finding a dodo bird, painting a continent, or driving your sister insane. So as you can see, there's a whole lot of stuff to do before school starts this fall. So stick with us, cause Phineas and Ferb are gonna do it all. So stick with us, cause Phineas and Ferb are gonna do it all. And that pretty much wraps up the main sequence phase. However, there is more information to be told, which unfortunately does not require me singing, but that may affect your enjoyment of it. But here it is. The main sequence is the best stage of life or time of year for all stars. In this stage, the star fuses hydrogen atoms to helium atoms. It releases the vast majority of its energy during the stage. Low-mass stars and high-mass stars spend their main sequence pretty much the same through fusion, but high-mass stars blow through red way faster than low-mass stars due to their much larger mass and much faster rate of fusion. And now we get to the giant phase. The giant phase is when the star exhausts its supply of hydrogen to fuse into helium, and then must begin fusing helium to continue existence. As a result of this, the star's outer layers begin to rapidly expand, with low-mass stars reaching the size of Mercury's orbit, and high-mass stars reaching truly titanic sizes. This is kind of like the last week before school starts in the summer, when you know that time is running out and that it's not going to be fun pretty soon. Here we reach another distinction between low-mass and high-mass stars. Low-mass stars never get dense or massive enough to fuse more than carbon, but high-mass stars are able to fuse elements up to iron. This might not seem important now, but it will be important in the future. High-mass stars become supergiants, as they could be considered giants in their main sequence phase. We now reach the post-giant phase. For high-mass stars, it's pretty simple. Their year ends with a bang, a supernova. They kind of just skip from August to New Year's in a flash. They supernova because the stars require a lot of energy to fuse elements up to iron, so they must become supermassive and super dense at the core. They pop like a balloon and explode like firecrackers. After the supernova, the remnants band together and they become a neutron star. Given an immense amount of time afterwards, they could become black holes. Low-mass stars are a bit more complicated. They don't explode. It's not that simple. The dense carbon-fusing core separates from the outer layer through a series of helium shell flashes. This causes the star to become two distinct parts, a core and an ejected envelope. This brief stage of the star is known as a planetary nebula, which is a misleading name. Over time, the ejected envelope spreads across an area roughly the size of the solar system, and could either become an interstellar cloud or a cool gas cloud. The core of the star goes on a much longer journey. First, it becomes a white dwarf. The dwarf shines off its stored energy and does not perform any fusion of its own. It's about the size of Earth, with some white dwarfs being even smaller. It has about half the mass of our Sun, or half the mass of whatever star it formed from. After some mind-boggling amount of time, the white dwarf runs out of heat and eventually stops glowing and becomes incredibly cold. However, this takes so long that we can't see any black dwarfs in the sky, and we'll likely never see one for the next couple of trillions of years. A little bit of context here, a black dwarf is what is theorized a white dwarf will turn into after fusion finishes and the white dwarf runs out of stored energy. In conclusion, stellar evolution is a wonderful and fantastic process that takes an incredibly long time, is the cause for everything that we can see and interact with in the universe, and is so very, very important. I thank you for watching, and I hope you have a good day.